Hi everyone, in this video I'm taking a look at question 12D part 2 of the 2020 Killara Extension 2 trial exam. So in this question we're told if n is not a multiple of 3, prove that x to the 2n plus x to the n plus 1 is divisible by x squared plus x plus 1. And this part 2 follows on from part 1 where you can use that result if you want. That's kind of where the question writer is guiding to then help with part 2. There is actually a set of solutions available, and the student who sent this through has access to those solutions, but it's quite common that you can be given the answer to a question, a mathematical question, and if those answers skip over a lot of steps and assume a lot of things, it's possible to still not really know how to answer a question even with the solutions right in front of you. So given that's the case for the student who sent me this question, I'm going to be quite deliberate to walk very methodically through my approach and not be quite deliberate about not skipping over steps. And the approach I'm going to use is going to be go right back to basics on quadratics. So whilst you could use your knowledge from extension 2 of roots of unity to tackle this question, I'm actually going to walk through an alternative that just really starts from basic quadratic formula concepts and then works through the proof step by step. So as we read in the question, what we're being asked to show is that x to the power of 2n plus x to the n plus 1 is divisible by x squared plus x plus 1 when n, when n is not a multiple of 3. And to kind of start from the very beginning for this question, this polynomial here will be divisible by this one if it's possible to write it out as x to the 2n plus x to the n plus 1 being equal to x squared plus x plus 1 times what I'll just write as other factors, all the other factors, which we can't really know in general because we're dealing with n here. But basically you can write a polynomial as a multiplication of x minus all the factors. Here we want to see, can we write x squared plus x plus 1 as a factor of this polynomial? If so, then that's how we show that it's divisible. So that's a basic idea. Now, I think to answer this, the question we can ask ourselves is, are the roots of x squared plus x plus 1, are the roots of this polynomial also roots of x to the 2n plus x to the n plus 1? I think if we can show that to be true, then we'll be able to write this polynomial as having factors that then let us write it in this form. So that's the basic technique. So basically to answer this question, we're going to find the roots of x squared plus x plus 1. We'll then substitute those roots into this polynomial, and if that also can be shown to be 0, then it must mean that they're also roots of this polynomial, and that's what will get us to our conclusion that we need to draw. So naturally, the first step that we need to do here is to find the roots of x squared plus x plus 1, and we do that by setting it equal to 0. So we can say when x squared plus x plus 1 is equal to 0, and this is where, as I mentioned, I'm going to go right back to basics and use my quadratic formula because this is a quadratic, it's a polynomial of power 2. So we can say x is equal to negative b plus or minus root b squared minus 4ac all divided by 2a. That's the formula that's no doubt been etched into the memories of all Extension 2 students out there. And so in our case, what we're dealing with, we've got an A, B, and C, all of 1, 1, 1, and 1. So substituting those in, we'll get -1 plus or minus root 1 squared minus 4 times 1 times 1 divided by 2 times 1. And that's going to give us -1 plus or minus the square root of 1 minus 4 is -3. And this is where we get into complex number territory, divided by 2. And this is why, as I mentioned, you could use your knowledge of complex numbers and roots of unity to tackle this question. But I'm going to use this fairly longhand way, just as an alternative to, I guess, what you could call the main solution, which is in the available to anyone who gets a copy of that Killara trial. So what I might do is I might define these roots. We've got two of them because it's plus or minus. So let's say let these roots be, and we'll define them, I'll define them as alpha and beta just to make them a bit easier to refer to later. So we'll say alpha can be -1 plus root, and here I should really simplify this to say it'll be root 3i given I squared is equal to -1. So I is the square root of -1. So that's going to be -1 plus root 3i on 2. That's going to be alpha. And beta we'll define as -1 minus root 3i on 2. So hopefully you've been able to follow along with that, just starting really simple using our quadratic formula. Hopefully as an Extension 2 student you'd be very comfortable taking the square root of -3 and writing it as root 3i. So now that we've got alpha and beta defined, I'm just going to do a few little side steps. I'm going to call them fun facts, and there's two fun facts that we can deduce about alpha and beta that will help us later on. So it's probably helpful to just lay them out now. So fun fact 1, and you probably wouldn't write it like this in an actual exam, but you might write something like a note or just lay it out. But let's have a look at what alpha squared is equal to. So I'm just going to do this the long way. Let's just square the whole thing. So alpha squared would be -1 plus root 3i on 2 all squared. So if we then square top and bottom, so this squaring this top bit would give us the first one squared, which is 1, minus twice the product, so 2 root 3i, plus the last one squared, so root 3 squared would be 3i squared, and denominator 2 squared is 4. So that's going to be 1, 3, since I squared is -1, 3 times I squared would be -3, so 1 minus 3 is minus 2 root 3i on 4, and I can divide top and bottom here by 2, so that's going to give us -1 minus root 3i on 2, and notice that's beta, so we can say that's equal to beta. So alpha squared is equal to beta. That's fun fact 1, and we can do basically the same thing. So I'll just do that now in terms of beta squared. So we'd then say that's going to be -1 minus root 3i on 2 all squared. So that's going to be the first one squared, which is 1, minus twice the product. These two negatives will become plus 2 root 3i. Plus 3i squared on 4, and again 1 minus 3 would be -2 plus 2 root 3i on 4, divide top and bottom by 2, so we get -1 plus root 3i on 2, and that unsurprisingly is alpha. So our first fun fact is that alpha squared is beta and beta squared is alpha. Now I might turn over for the second fun fact that will be helpful for us to work through. So fun fact number 2. This time we're going to look at alpha cubed. So alpha cubed we can write as alpha times alpha squared. Hopefully you can, that's no surprise to you in terms of breaking up this cube into 1 and 2. So that is going to be alpha times, now using fun fact 1, alpha squared is beta. So that's alpha times beta. And again, going right back to basics on quadratics, if you take the product of two roots, that hopefully you remember is equal to C on A when we're defining A, B and C in terms of what's sitting in front of each of the x squared, the x and then the constant. So they're all 1 for us. So C on A is equal to 1 on 1, which is just 1. So alpha cubed is equal to 1, and hopefully it won't come as any surprise that we can get the same thing for beta cubed, being beta times beta squared, which is beta times alpha, because remember we also showed that beta squared is alpha, and again that's just C on A, which equals 1. So our second fun fact is that each of the roots cubed is equal to 1, and that's going to come in handy as we now work through the detail of showing that the roots of alpha squared plus, x squared plus x plus 1, those roots, which we've defined as alpha and beta, we're now going to go about showing that alpha and beta are also roots of x to the 2n plus x to the n plus 1 when n is not a multiple of 3. So the question then becomes, well, how do we represent n not being a multiple of 3? And the way we can do that is, again, it's a bit longhand, but hopefully it's easy enough to follow. We can say if n is not a multiple of 3, then what we can say is that n will be equal to 3k plus 1, or n will be equal to 3k plus 2 for some integer k. So the idea is if you take some integer and multiply it by 3, then naturally that's a multiple of 3, but if you then add 1 or add 2, then you've no longer got a multiple of 3. Obviously you don't add 3 because then you're back into 3 territory. So basically we've got two cases. If we can show, well, let n be 3k plus 1 and see what we get, and then let n be 3k plus 2 and see what we get, then we've kind of shown it for n not being a multiple of 3. So let's now do that work. So case 1, let's have n is equal to 3k plus 1. And remember, our fundamental question now is, are alpha and beta roots of this polynomial here? So the way we can work that out is substitute alpha and beta into that polynomial one at a time. So we'll do alpha, then we'll do beta, and see if we get 0, because that means it must be a root. So let's start with alpha. We'll do alpha to the 2n plus alpha to the n plus 1. What is that equal to? Well, first we can substitute n is equal to 3k plus 1 there. So we get alpha to the 2 times 3k plus 1 plus alpha to the 3k plus 1 plus 1. Let's kind of simplify this. So we'll get alpha to the 6k plus 2 plus alpha to the 3k plus 1 plus 1. So that's alpha to the 6k times alpha squared plus alpha to the 3k times alpha plus 1. And here what I want to do is make use of this fun fact. I'd like to, in this case, get an alpha cubed in there because I know that that will simplify things because alpha cubed is 1. So I can write that as alpha cubed to the 2k times alpha squared plus alpha cubed to the k times alpha plus 1. And there we have it. We know alpha cubed is 1. 1 to the power of anything is still 1. So that's going to give us alpha squared plus alpha plus 1. And that is indeed 0, since alpha is a root of x squared plus x plus 1. So if you go put alpha in there, you know it must be 0. So alpha squared plus alpha plus 1 is 0. So what can we conclude? We can say, therefore, alpha is also a root of our x to the 2n plus x to the n plus 1. And one way we can think of that is therefore x minus alpha is a factor of x to the 2n plus x to the n plus 1. So that's good news on alpha. Now to finish this case off, we also need to show it for beta. Maybe I'll turn over for that. So let's have a look at beta to the 2n plus beta to the n plus 1. What's that equal to? Well, all we've done is wherever we had alpha, we've put beta. So we're going to do the same thing. We'll get beta to the 2 3k plus 1 plus beta to the 3k plus 1 plus 1. Now, rather than repeat all the steps that I just did for alpha in terms of, we're going to get to the same place because all we've done is put a beta here. So we could probably get that down to beta cubed to the 2k. So beta cubed to the 2k times beta squared plus beta cubed to the k times beta plus 1. So that's just same steps as what we did for alpha. And again, because in our fun fact number 2, we also showed beta cubed was 1, you can then have that same conclusion where 1 to the power of anything is still 1. So you get beta squared plus beta plus 1. And we know that's 0 since beta is also a root of x squared plus x plus 1. So same conclusion, that means beta is also a root of x to the 2n plus x to the n plus 1. And in other words, x minus beta is a factor of x to the 2n plus x to the n plus 1. So in terms of this case 1, what we can now conclude is that x to the 2n plus x to the n plus 1 can be written as x minus alpha, x minus beta times whatever other factors there are. We can't really work them out without knowing specifically k and therefore n, but we know that there could be other factors. But all we really care about is the fact x minus alpha times x minus beta. Since alpha and beta are those two roots of x squared plus x plus 1, we know that that would expand to then being x squared plus x plus 1 times these other factors. And remember, right at the beginning, we talked about how if we want to show that this polynomial is divisible by this one, then we can write it as having that x squared plus x plus 1 times the other factors. And that's exactly what we've shown here. So we can say, at least in the case of case 1, n being 3k plus 1, it is the case that x to the 2n plus x to the n plus 1 is divisible by x squared plus x plus 1. Now we haven't finished there. We now need to go through that process for case 2. So case 2 is where we let n is equal to 3k plus 2. Now we're going to do the same steps, so it's going to be very similar working, but there is a slight difference because the 3k plus 2 means in our simplifying we need to make use of, we're going to make use of fun fact 1. So I will work through it rather than just skip over it, because whilst the temptation may be to say, well, you're just going to get to the same conclusion, you do need to actually do the work if you want to kind of be sure. And also, if you were going to do this on an exam, you'd need to do it to make sure you get the marks. You need to really show the marker that you know what you're doing. So let's just work through those steps. So we'll start with alpha again. So alpha to the 2n plus alpha to the n plus 1. In this case, it would be alpha to the 2 times 3k plus 2 plus alpha to the 3k plus 2 plus 1. So let's simplify that. So we get alpha to the 6k plus 4 plus alpha to the 3k plus 2 plus 1. So like we did before, we'll go alpha to the 6k times alpha to the 4 plus alpha to the 3k times alpha squared plus 1. So I'll write that as alpha cubed to the 2k times alpha to the 4 plus alpha cubed to the k times alpha squared plus 1. And again, using the fact we know alpha cubed is 1 and 1 to the anything's 1, we end up with alpha to the 4 plus alpha squared plus 1. And so here we can't just automatically say, well, that must be 0. But what we can do is we can say, well, that's alpha squared plus alpha squared plus 1. And remembering from our fun fact 1 that alpha squared is beta, well, we can now substitute beta squared plus beta plus 1. And we know that is 0 since beta is a root of x squared plus x plus 1. So therefore we get to make our same conclusion that alpha is, and I might just be able to squeeze that on. We can say therefore alpha is also a root of x to the 2n plus x to the n plus 1, and that means x minus alpha is a factor of this. So exact same conclusion that we did in case 1. Now we need to work through beta, so let's turn over for that. So beta to the 2n plus beta to the n plus 1 would be equal to beta to the 2 3k plus 2 plus beta to the 3k plus 2 plus 1. And again, like I did before, rather than repeat all of these steps, we know we'll get down to well, wherever we had alpha, we're just going to have beta. So we're going to get beta to the 4 plus beta squared plus 1. So we'll say that's beta to the 4 plus beta squared plus 1. And that's going to be beta squared squared plus beta squared plus 1. And again, because we showed in our fun facts that beta squared equals alpha, we can then replace beta squared with alpha. So we get alpha squared plus alpha plus 1, and that is 0 since alpha is a root of x squared plus x plus 1. So therefore beta is also a root of x to the 2n plus x to the n plus 1, meaning x minus beta is a factor. And so now we get our final conclusion that x to the 2n plus x to the n plus 1 can be written as x minus alpha, x minus beta times these other factors. And like I did before, we know that since alpha and beta are roots of x squared plus x plus 1, this is x squared plus x plus 1 times our other factors. And that is what we had to show to be able to conclude that this is divisible by this. So that's all the work. So therefore, if n is not a multiple of 3, then we can conclude that x to the 2n plus x to the n plus 1 is divisible by x squared plus x plus 1.
Panic boom!
Alright, so that's how you get through that question. Now, as I mentioned before, this is not the only way you could do this. I think the solutions that were provided in the Killara trial, they actually just used roots of unity theory and actually made use of what you showed in part 1. So I quite deliberately wanted to show an alternative approach just because that solution is already available. And I think this solution, whilst probably longer in terms of the amount of working you have to do, I think maybe there's a better chance of, perhaps if you're struggling with the roots of unity approach, this approach you might understand, because fundamentally what I've done is I've just gone right back to the basics of the quadratic formula, which, you probably learned in year 7 or 8, who knows, but you would have known this for a long time. This should be quite, you should be quite comfortable with the quadratic formula and the idea of working out the roots and knowing that x minus each root, you can write them as factors, and that's really all I've done. I had to work through quite a few steps to get there, and maybe it might not have been completely obvious to think about these fun facts, although the reality is, as you work through, you have to eventually grapple with what's alpha squared and what's beta squared and what's alpha cubed and what's beta cubed, and as you can see, it's not a huge amount of work to work those out. So you might not have as cleanly just put them as a side step to start with, but you would have got there eventually. And from there, it's just kind of, pretty simple algebra. So hopefully, something you've been able to follow along with. And hopefully you found that helpful. And tick boom.